Today I will be talking about finding, finding components and angles of vectors. Now this would be pretty helpful in like physics or something like that, or if you want to find the angle between vectors when you're doing dot product or cross product. But I'll just be showing you how to find the components and the angles. I'll start with the angle. So let's say we have a typical XY graph. Name this positive X, positive Y. And let's say we have a vector at about here. And the components of this vector. So we're going to give the components first, and then we're going to find the angle for this one. I'm trying to find theta here. So let's say the components of this angle is, I don't know, 3 square root of 3. So in order to find the angle, or this angle, theta, you have to remember that these components are quite literally, let's say, the x and y values for now. So you can think of this as just a coordinate. And if this was a coordinate, that means that the x value is 3 over here, and the y value is 3 square root of 3. Now, look. Doesn't this look familiar? This looks like a triangle. So what can you use? You can actually use the trigonometric functions, or trigonometric ratios. So you have the opposite value of this theta, and you have the adjacent value. Which trigonometric function has opposite and adjacent? It's tangent. So we can put tangent of theta is equal to opposite over adjacent. And we can plug in the opposite and adjacent values. So opposite value is 3 square root of 3, and the adjacent is 3. And I don't want to simplify this, so we can just leave it as that. And how you can isolate theta is by using the inverse of tangent and wrap it around the entire thing. So when you do one thing to one side of a equation, you have to do it to the other side as well. And what happens is actually theta gets just left behind. When you inverse tangent a tangent, you just leave behind the theta, as well as a sine value. When you inverse tangent a sine value, you just get left behind theta. Or if theta was some specific value, like let's say 60 degrees, you get left behind 60. So whatever inside the, I guess, parenthesis of the inner sine function, you will get the angle or the radians when you inverse tangent, or inverse function, the trigonometric function. So we get left behind that theta here, and all we're left with is inverse tangent of 3 square root of 3. And it turns out that this answer right here is equal to 60. You can plug this into your calculator to solve this. Or if you have good understanding of the unit circle, you could just be able to solve this in your head. But the angle here for theta is equal to 60 degrees. And how you would just represent this is, well, you would say 60 degrees north or 60 degrees above the x positive axis, because right now this angle is right against this x-axis right here, or the positive x-axis. So you can actually use inverse tangents to solve for the angles of vectors. Now let's say you want to solve for the angles between vectors, and that's typically what you're going to be doing. So you have an angle here, we have a vector here, and let's say you have a vector here. And I'll give you the components of these vectors. Let's give it some random arbitrary numbers, 4 and 5. And let's give the green vector, I don't know, 10 and 3. So now that we have that, how do we solve for the angle right over here, theta? Well, first you need to solve for the two individual angles that these two vectors make. And we'll call this theta 2, and we'll call this theta 1. So theta 1 is going to be the angle between the green vector and the positive x-axis, and theta 2 will be the angle between the red vector and the positive x-axis. So how do we do this? Well, let's use inverse tangent. As we did before, inverse tangent of the opposite values, and I can actually start from the beginning to make it easier, but you'll soon realize that you just find the theta value by inverse tangenting these. So let's put tangent theta, and we're going to solve for the red one first. Actually, let's solve for the green one first because it's theta of 1. Inverse tangent theta of 1 is equal to the opposite value, which is 3. And for the red, going to be a lot of overlap here. For the red, it's going to be 4 and 5. So inverse tangent of theta 1 is going to be opposite over adjacent. The opposite of theta 1 is 3, and the adjacent of theta 1 is 10. And we're going to inverse tangent both sides to be left off with theta inverse tangent of 3 over 10. And let's plug this into a calculator. I'm going to grab a calculator, actually. Okay, inverse tangent of 3 over 10 is 16. I don't like the look of that theta. 16.699 degrees. And then now let's do the theta of 2. So let's just start off with theta of 2. Because you already know you just inverse tangent the opposite and adjacent values. I'm like, you don't have to start off with a tangent and inverse tangent both sides. So you don't have to start with this function right here and then inverse tangent both sides like this. You don't have to do that. You can just literally just start off with the angle and inverse tangent the opposite and adjacent values. So the opposite of theta 2 is 4. And the adjacent is 5. Okay, that doesn't look a lot like 5, but let's just say it's 5. So once we have that, we can actually just find theta of 2. So I'll plug that into the calculator. 4 over 5 is equal to 36.65 degrees. So how do you find the angle in between the red vector and the green vector? Well, the angle between the red vector and green vector, let's just call it theta, regular theta. So now that we have these two values, and let's actually highlight them. Now that we have the two angles that these two make between the positive x-axis, we can actually just solve for regular theta by subtracting theta of 2 by theta of 1. And the reason why is because this theta 2 right here goes all the way down to the positive x-axis, and this O of 1, or theta of 1, just blocks, is just the the extra part that we don't need. So when you subtract O of 2 from, not O of 2, theta of 2 from theta of 1, you get this angle right here, regular theta. This one. So let's go ahead and do that. Theta of 2 is 36.65 minus 16.699. What does that equal to? Time for the calculator. 16.699. And you get 21.951 degrees. So that is the final answer. Let's move this. So what we did first here was find the angles between both vectors on the positive x-axis. So we found theta of 1 and theta of 2 over here, represented by the colors, and we just subtracted them from each other to get the angle between the two vectors. So first we found the angles that the vectors make with the positive x-axis, and then we subtracted them to find the angle between each other. And you can also do this with the positive y-axis. I mean, if you wanted to do this with the positive y-axis, you would change the adjacent and opposite values, but you can still find it with the positive y-axis. Let's say the vectors were, I don't know, on this other side of the graph. You could still find it comparing with the negative x-axis. You can still find the angles, and with a little bit of logic, you'll be able to solve for the angles between the vectors. So it's not only the positive x-axis that you're comparing it to. And also, when you have angles between vectors, quick side note, when you have angles between vectors like this, you don't measure the longer angle. You always measure the shorter angle. And what I mean by that is you'll measure this angle. You'll measure this angle, not this one that stretches all the way. Okay? So let's say you have, like, I don't know, an angle that's almost 180 degrees. You measure the shorter one here, not the one that loops all the way around like this. Okay, let's find the components. So when we're finding the components of a vector, typically you're going to be given the magnitude and the angle that the vector has. So let's say we have a vector that looks like this. Actually, let's say we have a vector that looks like this. And we're given the angle 55 degrees. and we're giving the magnitude. Magnitude is represented by like an absolute value symbol, I guess you could say. We'll call this vector v. So the magnitude is equal to 10. So absolute value symbol over a vector, the name of a vector, the variable of a vector, is the magnitude. So let's say this makes a 55-degree angle with the negative x-axis. What do? Well, we can use the sine and cosine functions. So let's go ahead and do that. Sine of theta, or sine of this angle right here, whatever angle we're comparing it to, is equal to opposite over hypotenuse. And we actually have the angle. So we have 55 degrees here. And we also have the opposite. We don't have the opposite value, but we can actually solve for it. We have the hypotenuse. The hypotenuse is basically just the magnitude, is it not? This is a triangle, remember. This is the opposite value, and this is the adjacent value. And the hypotenuse is up here for this triangle. So since we have the hypotenuse, we can actually just plug in the hypotenuse value, and then we can isolate opposite. So how do you isolate opposite? You multiply both sides of this equation by 10, and then you get sine 10 times sine of 55 equal to opposite. Now this isn't an O, it just looks weird. But once you plug that into the calculator, you get opposite is equal to 819. Now, don't forget the negative values, because where this vector points to on the axis, or the plane that you're comparing it to, or basically just this graph right here, wherever direction this angle points to, it's very important to mark the right negative or positive values. So right here, we solve for the opposite value, which is the y value. And since we are still in the positive y side of this graph, or quadrant 2, we're in quadrant 2 here, the y values are positive. So 8.19 is going to stay positive. Let's solve for the cosine. So cosine of theta is equal to adjacent over hypotenuse, and we have the angle value, which is 55. Now we have to get the adjacent value, but we don't have that. Do we have the hypotenuse? Yes, we do. Hypotenuse is the magnitude, so the magnitude is 10. Multiply 10 by both sides of this equation, and then you get the adjacent, which is left behind, isolated. And then now all we have to do is solve for 10 cosine 55. 5.74, let's just round, is equal to the adjacent value. Now, in quadrant 2, the x value is always negative. So the adjacent value must be negative here as well. And that's why this is turned to negative. So the components of this vector, v of x, is equal to negative 5.74, because that is the adjacent value. That's why it's the x value. And yeah, I'm going to erase this x. And v of y is equal to 8.19. And remember, the reason why the x value is negative is because we are in quadrant 2 for this vector here. And the x values are always negative here. And you don't even have to memorize that. You can literally just graph negative 5.74. You go a little bit to the left here, let me guess, and you go up on the y value 8.19, and you get some point up here. And that looks like the vector that we just graphed. Now, if you had this, if we change this to positive, what would happen? Well, the vector wouldn't look right, because if you go to the positive x value, 5.74, you're going to go somewhere here. You go up 8.19, and you get this. Does this vector look like that vector? No, they're completely different. So make sure you don't forget the negatives when you are finding the components of vectors. Let's do one more problem. So let's find the components of. We can find the components in the angle, maybe. Now I'll just stick with the components for now. Let's have a vector facing here named v. Let's call the magnitude 25, and let's say that the angle it makes with the positive, the negative. Let's change it to negative. Negative y-axis is, I don't know, 25 degrees as well. So try to solve this yourself. If you can't, it's fine. I'm going to solve it right now. So I can label the axes right now to make it easier for you. But the opposite value is on the opposite side of this angle, which is this one right here. And the adjacent value is sitting adjacent to the angle, 25 degrees. Hypotenuse is 25, because we have the magnitude of this vector. So let's use sine first. So sine of theta is equal to opposite over hypotenuse. Let's plug in the values that we have. We have sine of theta is equal to opposite. We don't have opposite. We do have theta though, so maybe I should have written that down. Theta is 25 degrees, and the hypotenuse is 25. We isolate the opposite variable to get 25 sine of 25 to equal opposite. And then when you plug that into the calculator, 25 sine of 25 is equal to 10.57. Let's go ahead and find the adjacent value. Cosine of theta is equal to adjacent over hypotenuse. We'll plug in whatever variables we have, whatever values we have here. Cosine, we have the angle 25, so we plug that in. Adjacent over hypotenuse. Hypotenuse is the magnitude of the vector, so it is 25. And we just isolate the adjacent value here. A. And now when you plug cosine of 25 into the calculator, you get 22.66. About that. Now remember, we are in quadrant 4 here. What does that mean? Well, you can label in the axes, but if you want to know, that means the x value is positive. Sorry. The x value is positive here, and the y value is negative. So, what is the opposite value here? Keep in mind, the opposite value from what we've done before has always been the y-axis. Now the opposite value is the x-axis, or the x value. Let's mark this down for now. So, the opposite value is 10.57, so 10.57, right over here. And what does that mean? That means, since we are in quadrant 4, the x values are positive, so the v of x value is 10.57. How about for the adjacent values? Well, the adjacent value is on the y-axis. Is it not? So, what do? Well, we're in quadrant 4 for this vector. So, the y value will be 22.66. Now, is it negative or positive? We are in quadrant 4, so 22.66 is negative. And that's how you solve for the components and angles of vectors. If you have any questions, put it down in the comment section.